I think this is page 20 of your unit handout. It's the final section that we're going to be looking at in chapter 4, which is applications of extreme values. Sometimes this is called optimization problems. Sometimes it's called maximum and minimum problems. Most of the problems we do today are going to in fact be problems that you could have done in Math 20 by creating a quadratic function and then completing the square to determine where the vertex is, because the vertex of a quadratic function tells you where the maximum is if the parabola opens down, tells you where the minimum is if the parabola opens up. However, even though most of what we do today is about parabolas, it's not always going to be that way, all right? So the idea here is we're trying to determine conditions necessary for things to be optimized. The word optimized means to make them as large as possible or as small as possible. In other words, we're trying to maximize or minimize things. So sometimes in economics and other areas of study, it happens a lot in physics. It also happens in chemistry and bio, but mostly in physics. We have certain quantities that mathematically can be optimized. They can be as large as possible or as small as possible. You can come up with a lot of different situations. The classic example from Math 20 The classic examples in Math 20 would be where you have a certain amount of rope and you're going to create a partition that's rectangular in some way, and you want to maximize that area. Or the classic revenue problem, which we're going to get to. There's another example in Math 30 that we're going to talk about right away. But you've seen problems like this before. Here's one that you haven't looked at before, but it's a classic calculus problem. A company that designs soup cans wants to build a can that holds all of the soup, but at the same time minimizes the cost of materials. I mean, I think that's common sense. If you're running a factory or a business, you want to minimize your costs. So I'm going under the assumption here that the can is a traditional shape. It's a cylinder. And what I have up here are 3 different cans. And it's hard to visualize volume and compare volume to dimensions. But I will tell you right now that I've used a scale diagram here, and these 3 cans all have the same volume. So it's possible for me to make a can that's very, very tall to hold the soup, hold a certain volume of soup. But because it's very tall, I don't need the top or the bottom to be quite big. It's going to be a very narrow tubular shape. On the other hand, I don't know why on earth you would want to make can C, but I could make can C by making the radius of the can absolutely phenomenally large, and then I just need a very, very shallow can. I mean, I could make a can that's 4 meters in diameter, right? And it would just have this slick of soup, assuming that it wasn't lumpy soup. This slick of soup that would give us the right volume, but that would be a waste of materials. And in all of these, it turns out the volume is, based on the ruler and the scale diagram I used, 30 cubic centimeters. So if you were to find the volume of any of these cans, volume is, for a cylinder, pi r squared h, whoops. Because a can is a regular solid, the area of the bottom is pi r squared times the height. You would discover that you get 30 in all of those. But somewhere in the middle, and it might not be exactly what I've drawn for can B, somewhere in the middle is a can that minimizes the amount of materials. And again, as a business person, if you have less materials, you have less cost, you have more profit. So another example, and this is one directly from Math 20, I hope you remember this kind of idea, that if you were selling tickets to some arena or some event, if you increase the ticket price, what happens is the people who are still willing to pay, you get more money from them, but you get people who are not willing to pay, so you lose customers. But what happens initially is the total revenue goes up, even though you're losing people, because you're increasing the price. Sooner or later, though, you lose so many people that the revenue hits a peak and it starts to come down. So what economists and the concert promoter would be interested in is, well, how much should I charge in order to get the most money out of people? Not the most money out of each person, the most money out of the population of people. And you would be trying to maximize it. what we want to think of here when we solve these problems is always setting up a function that has two variables. One of the variables is the thing you want to maximize or minimize. So if we can define the surface area of the can as a function of the radius, then the minimum value of the function could be found using differentiation. If you can come up with a formula that says area, I use A instead of SA, area equals, and then there's a function of R, then you can find dA dr and set it equal to 0 and determine where that minimum is. Right? That point is going to correspond to the minimum surface area, but more importantly, there's what's called an optimal radius. It's the radius that you want to set your machines to build the cans to create the minimum surface area, which is minimum cost. And I didn't put it up here. It occurs to me I should have. I hope it's obvious that at this point what we're talking about here is the derivative as a critical value of x at that point. And the critical value of x is going to be that optimal radius. You know what? I'm going to change what I just wrote. Sometimes it's okay to not be technically correct, but in math you should be technically correct whenever possible. Right? That's what we would be talking about here. And it has a critical value for the radius. The tough part is going to be finding that function. And by the way, I hope you understand that even though I've drawn this, we're not going to solve these graphically. We're not going to look at a graph and find the minimum. We're going to find it on paper. On the other hand, if you can describe revenue as a function of the ticket price, or I've got increase in the ticket price, we'll worry about that later. And it turns out that the function looks like this, then what we've got is a maximum revenue that occurs at an optimal change in the ticket price. And at this point, of course, the derivative of revenue with respect to, I'm going to use I for the increase in ticket price, would have a critical value for the increase in the price of the ticket. Whatever that number is, that's what you want to do, because that will produce the most revenue. I am pointing out here that these are not necessarily parabolas. I just drew them so they look like parabolas. So what you're always trying to do here, and I've already mentioned this, but you're always trying to create a function that if you graphed it, the y coordinate or the y variable would be the thing you're trying to optimize, and then x is anything else that determines the value of y. So these would be the graphs that we would be looking at for the two illustrations. All right, we're going to start with a warm-up, and you've seen this warm-up if you've taken my Math 30-1 class. Or I always dislike the fact that you're told in textbooks, and they do this all the time, you take a piece of cardboard or something and you cut out the corners, and you actually cut them out and you throw them out. Well, I'm not going to cut them out to show this to you. I hope you understand that cutting them out is kind of a bad idea. If you just cut out part of each square, then when you fold this thing up, what you're going to get, must have spilt water on this, what you're going to get is a box. I'm running out of things to do here. Run out of hands. You're going to get a box, but the important thing is if you leave the flaps on, then you can glue this, right? If those flaps aren't there, then you just have two edges coming up and somehow magically you're going to join them. It's not a very stable box. You're going to have a written response question in the week that we get back that's a little bit more complicated than this. But this is the basic idea. And I hope you understand that if I fold up the flaps here, I get a particular volume for that box. I'm not folding over the flaps on the side to glue it. But that volume is determined by how big this square is. If I cut out a larger square, I take and I cut the squares this big, and I fold this all up, I'm just going to get this puny little, I would have to crease it, but I'm just going to get this puny little box when I fold it all up. So the idea here is the volume is determined by the size of the length of the cut. And I have another one here with little tiny squares, but you get the idea, I think. You remember that from Math 30? And if you're in 30-1 right now, we did that already, yeah. So this box is going to have dimensions that's determined by the fact that the paper is 74 by 30 to begin with, and we're cutting out X. So here's the problem. If we remove 1 centimeter from each corner, whether you cut it out or fold it up, it doesn't matter. The original width of the paper was 30 centimeters, and the original length was 74 centimeters. I don't think I've forgotten those numbers from the previous page. I'm good. So if I cut out 1 centimeter from each corner, what that's going to leave me with is 28 centimeters for the width when I fold this up. Going back to this diagram, we've done this before, but I hope you understand that this distance here, which is the width of the box, is this distance before everything is folded up. And that distance on the right-hand diagram is 30 minus 2x. It's minus x minus x. So I have to take off that centimeter from each edge. Here it's going to be 72 centimeters. If I were to take off 3 from each side, then I would go 30 minus 3 minus 3. Help me out here, 24. If I were to remove 5 from each side, then I'm really removing 10, and I get 20. And I'm not so sure we need to populate this whole table, okay? I'm trying to teach you how a junior high student might approach this problem, okay? And we're removing 3 and 3 from 74. That leaves me, I believe, 68. If we remove 5 and 5 from 74, that leaves me with 64. By the way, the height of the box, if it's not clear, I'm going to go back to my diagram here. The width of this box, and we're talking width and length and height here because we're after volume. The width of the box is that, which is found by taking 30 minus 2 of the cuts. The length of the box, once it's completed, will be this, which is explaining why we're taking 74 and cutting off x and cutting off x numerically. But what's important is that the height of the box, this, will be that, because that's the edge that's being folded up to create that third dimension of depth from the top down. So if I asked you to determine the volume, you would have to take 28 times 72 times 1. You would have to take 3 times 24 times 68, etc. Well, let's just do a couple of quick calculations, and then we can, dispense with the junior high-ish approach and just do it algebraically. So we have 28 times 72, 3 times 24 times 68. I hope nobody's bothered by the fact that I didn't include the 1 in the first calculation. And this next one is going to be 640, I believe. 6,400 rather. Right, 6,400. So 2016, 4896. I did not want to do that. This is 2016 cubic centimeters, 4896. And you said 6,400? Is that right? That's really enough to demonstrate my point that cutting out a centimeter from each corner in this situation produces a certain volume that's nowhere near the maximum. Cutting out 5 from each corner produces a larger volume, but it's less than cutting out 3. So there's some point in between, presumably 3 and 5, that would produce a maximum volume. Are you with me on that? Oh, it's still going up, isn't it? My mistake. What about if we went 7? Does it go down at 7? It does. So at 7, this would be minus 4. This would be, I believe, 16. This would be 60. And can you tell me what you get for the volume here? 5,600. Okay, so my mistake. I thought we had hit the hit and passed the maximum. So 6,400 is bigger than 4,896 and bigger than 5,600. So presumably between 3 and 7, there's a number. But we want to make this more general. And since it was 30 centimeters and we're subtracting 2 of those, in any case, the width is going to be 30 minus 2x. We started off with 74, and for every case, we're subtracting 2 of those x's. So what's the volume all the time, regardless of what we cut out? The volume is x times 30 minus 2x times 74 minus 2x. This is a formula for the volume. And again, I may have even last semester in my Math 30 given you a written response assignment with that problem. Does that ring a bell? It does. Okay. All right. As the table shows, the volume depends on the size of the square cut out. Write volume as a function of x. Well, volume as a function of x is equal to x times 30 minus 2x times 74 minus 2x. I don't know what you remember from Math 30-1. This is probably about 5 months ago for polynomials from last semester. And if you're in this semester, I didn't give you one like this yet. I may or may not. I don't know what you remember from last semester, but we would have solved this by using a graphing calculator to find the maximum, because you have no way of finding the maximum of a cubic polynomial function last year or last semester, but you do now. Let's expand this out, and then we can talk about what we're going to do. When I expand this out, I'm going to have to take these two binomials and multiply them together. So when I do that, I'm going to get 4x squared. But I need to also multiply by x, so I'm going to get 4x cubed. When I multiply this out, and you will have to double check my math here, my outer will be 148x, and it will be negative. My inner. My outer will be negative 60x. How's my math there? When I add those two terms together, I get negative 208x, but I'm multiplying by x, so I have minus 208x squared. And when I multiply out the 30 by the 74, I get 2220. Okay. But I'm multiplying by x, so this is the function in simplified form. It's a cubic function for the volume of the box. Conceptually speaking, I hope you understand that if there is a maximum volume, then there is some point on the graph that's at the top of a local region or a local hill. And I hope you understand that that's a maximum, which means there's a critical value of x. So now we're doing what we did yesterday. We have to differentiate and find the critical value of x. There's going to be one exception here. We're done B. Right, that's B. Use the function to determine the size of the cutout. Just help me out, please, and let me know if my memory is solid on that. It is. So how do we do that? We find the derivative, v prime of x equals 12x squared minus 416x plus 2220. Now, those are all even numbers. Can you just double check my multiplication? I'm pretty sure that's okay. Those are all even numbers, so we can factor stuff out. We always want to look in factored form if at all possible. I'm going to just jump right in and say, does 12 divide into 2220? It does. Wow. Does 12 divide into 416? Rats. Does 6 divide into 416? 4 is another number. I'm looking for factors of 12 that are bigger, as big as possible. 12 doesn't work. 6 didn't. 4 does. 4 does. So I can factor a 4 out to make my algebra easier. 4, that leaves me with 3x squared minus 104x plus 555. Okay. I'm going to go out on a limb this time and say, I don't think that's factorable. But maybe it is. And I see most of you working on your calculator here to find, I'm assuming b squared minus 4ac, and I'm seeing people shake their heads, it's not factorable. I mean, I hope you can appreciate, if this were factorable, I must have put a lot of thought into choosing the right numbers to make this all factorable in the end. So it's not factorable. But what did you get, Annalie, for the discriminant of b squared minus 4ac? 4156. Boy, that really looks like it should be a perfect square, but it isn't apparently. So, but the point is, and this goes back to grade 11, your discriminant is positive, which means there are solutions. But before we find them, this is different than the stuff we were doing yesterday. Because yesterday, it was just a pure mathematical function. This is an application. There's a domain here. What is the domain of this function? I better write that over here where we had the actual function. We're talking about the domain of the function. I don't want you to look at this and go, well, geez, it's a cubic polynomial function, which means x is any real number, because it has applications. X here is a length of a cut. Do you know what the domain is, Jack?
X cannot be larger than 15, and it has to be larger than 0.
Excellent. The domain is that x has to reside between 15 and 0. First of all, if you're going to get a volume, you need to have a length that you're cutting out. You can't cut out 0. You can't just look at the piece of paper and expect to have a volume. And why is it that we can't even reach 15? We can get close to 15 but not reach 15.
Because then once you cut out 2 boxes the size of that, it will completely negate the width, which means it will be a 2-dimensional shape.
Perfectly put. If I go back to this and I take 15 and I cut 15 off here and I cut 15 off there, so I'm cutting out 15 by 15, this is going to be a gluey flap thing that goes around the corner. But when I fold it all up and I do the same thing on the other end, I don't have a box. I just have a 2-dimensional fold of paper. That's all I have. And that makes our life easier because when we find the critical values of x here using the quadratic formula, we can exclude any of the critical values.
At this time, we are now in a hold and secure. We are now in a hold and secure.
What's going to happen here is if we get 2 critical values of x and one of them, listen carefully to this logic. If one of those critical values of x is outside of the domain, then the other one must lead to the answer. I'm never going to ask you a question that says, find a maximum if the maximum doesn't exist, okay? We are, however, going to do a first derivative chart this one time with this question to demonstrate that it is a maximum. So what do we get here? We get negative b, and again, I'm going to use the factored result here. I'm not looking at the 4. Negative b is 10 plus or minus root 4156 all over 2a, which is 6. I'm going to go out on a limb. Well, I don't know. It's not 10, it's 104. And I was just looking at the numbers going, it can't be 10. It's 104. I'm going to go out on a limb here and, well, I don't know. Is 4156 as a square root more than or less than 104? It's less. So we actually have two valid positive numbers. One of them will be 104 plus root 4156 over 6, and the other will be 104 minus root 4156 all over 6. See if you guys are on top of things here. Why is it that this is going to be kicked to the curb? I'm pretty sure it's going to be. It's probably going to be greater than 15. I don't know what root 4156 is. It's in the range of around 20-ish. What is it? 64. Oh, really? Okay. 64. So if I take 104 plus 64, well, that's obviously, I'm in the 160s divided by 6. I think that's more than 15. So that's thrown out. What about 104 minus that 64 point whatever, all divided by 6?
About this,
Yeah?
I think it's wrong. 2,200.
You think the 4156 is not correct?
No, the 555 up there. Isn't it 2,200?
But we took out a
Four.
4.
It should be 550.
Is it 550?
Not 55.
It was 2,220. So it was a 5.
Yes. Okay. Thank you. I knew something was wrong.
Okay, so we'll just make sure here. 2220
Okay.
divided by 4 is 555? Okay. Will, have you got this number here?
Yeah, that's 6.58.
6.5. That must be the answer. That's the only critical value. I'm just going to put equals approximately 6.58 here. This is the only critical value for x. So from a logical standpoint, I wouldn't ask you to find a maximum if there was only one critical value and it didn't correspond to a maximum. I want to be clear here. This other number is not a critical value because it's not in the domain. By the way, there are two other critical values. What are they, Jack?
They'll be when x equals 0 and when x equals
But I hope you see that we can quite quickly discount those. They're critical because the derivative is not defined there because that's where the function begins and ends, and they're ludicrous results, right? The function isn't even defined there. So if you were to do a derivative chart, and we'll get to the answer to the question in a second, but this does say, use a first derivative chart to confirm this. You would go from 0 to 104 minus root 4156 all over 6, and from 104 minus root 4156 all over 6 to 15. When I say to 15, we don't include 15, right? And then because the thing is not factorable, across the top, we just really put the whole derivative. I'm going to go by memory again, so I'm asking for your help here. Is that the derivative in factored form? So what you have to do a bit of grunt work here. It's not just looking at it. You said this was 6.58. So a number that's in there is 1. In the first interval, the number 1 is in there, between 0 and 6.58. That's a pretty easy thing to put in. And if I put 1 in, I'm going to get 555. I'm going to get 441. I'm going to get 438 times 4. Well, it's going to be positive. I don't even need to go any further. And here, I'm not so sure if there's a nice number that's easy to work with, but you might want to choose 7 or 8 or 10 or I don't know. But I will leave it to you to confirm that if you put a number in the derivative between the 6.58-ish and 15, you're going to get a negative. Which means, I'm just going to erase this, didn't plan out my workspace very well. It means that the derivative d volume dx is positive. Well, the whole thing is the derivative, right? I don't think we need another column. And negative, which means volume increases to that point and decreases after that point. So it's a maximum. We haven't answered the question. All we've said is the ideal size of the cut is approximately 6.58 centimeters. To find the volume, you have to put that back in for x in your original function. Or go back to the beginning and take 6.58 times 30 minus 2 of those times 74 minus 2 of those. And I see a couple of you clicking away on your calculator. I don't really feel like doing it, but if we can get an answer, it would be nice for completeness' sake. Does anybody have a decimal answer? It doesn't have to be precise. Probably the least important part of this question is getting the final answer. Sasha?
6,741.5.
6,741.5. So should I say 6,742 or 741?
742.
Okay. 6,742 centimeters cubed. I think if you were to go back and look at that table, and can I get a seconder on that? Okay, good. I think if you were to go back and look at that table that we constructed, that makes sense. You know, we saw, just roughly speaking and going up by increments of 2 centimeters, it was peaking in the 6,400 range, so more specifically 6,742. Any questions with that example? All right. We're going to not burn through these, but as I said, I'm choosing examples that we have done before. Now, you know, if you didn't have me as a Math 20 teacher, maybe you didn't see this particular problem, but you should know how to work it. A farmer wants to make a rectangular pen for his snakes, poodles, and pit bulls. This farmer has 600 feet of chicken wire. I'm not sure he has thought this out very well because chicken wire has a bunch of holes in it. If the snakes are really tiny, they'll just slither through, but we'll just go with it. He's going to use one side of his barn, and this is his plan. So these lines that are to the right of the barn are the 600 feet of chicken wire. We're going to start off by recognizing, and we saw this in some related rates questions, but not all, that in max-min problems, there's almost always an equation of constraint. No matter what this guy does, whether he makes this distance 10 meters, 10 meters, 10 meters, 10 meters, was it meters or feet? Feet. It was 600? So, bless you. 10 feet, 10 feet, 10 feet, and he decides to make this 560 feet long, assuming the barn is long enough. Doesn't matter. If he decides to go 100, 100, 100, 100, and 200 here, do you see where I'm getting 200 from? Okay. There's a constraint, and the constraint is that this distance, I'm going to call it W, and this distance L, are related because L plus 4W has to equal 600. This is the equation of constraint. You might argue, well, does he have to use all the chicken wire? Common sense says if you want the most area, you're going to go with most wire. So this is the equation of constraint. Now, you don't have to have that right away. What you could do is dive right in and say, let's come up with an equation defining what's to be optimized. Area needs to be as large as possible, so it's going to be area as a function of something. I'm not going to use function notation. Well, how do we find area? Look at the diagram. Area is length times width. And I mean, I hope you understand why we have 4W in the equation of constraint. It's like a perimeter, but it's not a perimeter. So here's the issue, and I hope this makes sense. If you're trying to connect what we're doing to derivatives, then A has to be a y variable, and you need a point where dA d something is 0. You need a point where there's a maximum A. But the concept of a graph, this graph that you're looking at here that's incomplete, the concept is only valid in most math, even first, second, third year university. A graph is only really valid most of the time if it's two variables. Y is a function of x. So one of these variables needs to go, and it's up to you which one you want to get rid of. I hope that you can look at your equation of constraint and see that looking at that, it's easier to rearrange this for L than it is to rearrange it for W. It's not hard to rearrange for W, but do you see that if I rearrange for W and sub into my area formula, I'm going to have fractions? Okay. So go with whatever's easiest. Area equals L, which is 600 minus 4W, times W. The rest of this question is going to take us 2 minutes. Well, don't start timing. I might be off on that. Lucas is going to time me. If I expand this, I get negative 4W squared plus 600W. What we need to do is find dA, dW, so that we can identify the critical values of W, because that's where the area will peak, or valley, but it's going to peak. Well, this is negative 8W plus 600. This is literally the definition of taking candy from a baby. It's so simple. I wouldn't set it equal to 0 and rearrange it. I would just factor out negative 8. You could set it equal to 0 and solve it, but if I factor out negative 8, 75, negative 75, boom. I'm pretty much done. Don't hold me to the 2-minute thing. But the only critical value of W is 75, which means that's the solution to the problem. From here on in, we're not going to do a derivative chart for all of these unless, and we might bump into it, unless you get multiple critical values. Then you're going to have to do a chart to suss out which one is right. So that means that going back to our diagram, this is 75. The rest of this is, you can figure this out. L is 600 minus 4 times 75. Or you could figure it out just by looking at the diagram. I think that's going to be 300. Well, now if you were asked what's the maximum area, take 75 times 300 and get 22,500. So A max is 22,500 square feet, which is not too shabby. That's a fair amount of room for his vermin to slither and walk around in. He's planning this, and then he has an idea. What if he does this? Now, this is kind of a bad design, but You might look at this and argue that this is a bad design because maybe he only has one opening or one door to the barn and it's there. So you can't necessarily access all three at the same time. You're going to have to put doors somewhere to go from enclosure to enclosure. But you think, so is it going to change if I do it this way? It's the same idea, isn't it? But now what we have is 3L plus 2W equals 600 as the equation of constraint. We're still maximizing area, so we still have to get rid of L or W. And I think it's a coin toss here. I don't think it really matters. Because if you rearrange for L, you're going to have thirds somewhere. If you rearrange for W, you're going to have halves. I'm going to rearrange for W. Two W equals 600 minus 3L. So W equals 300 minus 3 halves L. Again, if you knew how to do these in Math 20, if you knew about the derivative, you wouldn't have to worry about completing the square. Does my rearrangement for L look okay? All right, so we're going to have L, which is 300 minus 3 halves L. Nope. We're going to have L times W, which is 300 minus 3 halves L. So I guess in the previous question I had A as a function of W. Now I have A as a function of L. Expand this out. Don't forget, and I'm being very sincere here, don't forget to differentiate it. Because sometimes what happens is you go through all this work, you lose sight of what it was you were doing, and then you just start setting things equal to 0. Yeah, that looks okay. Let's differentiate it. dA, dL. So unlike related rates, we're going dy dx, not dy dt and dx dt and dp dt. Negative 3L plus 300. I'm actually quite glad we rearranged it for L or for W, because if we had thirds in there, then I would have fractions in my derivative. Although that, you have to look pretty far down the road to see that's what would have happened. Take out a negative 3. You get L minus 100. Well, again, in terms of the derivative dA dL, there's only one critical value of the variable L, which is 100. If you were to construct the first derivative table, you would confirm that prior to 100, the derivative is positive, which means the function is going up, and after, the derivative is negative, which means the function is going down, which means you have a maximum area. This is 100. A little bit of thought, I think this is 150. I didn't use the formula for W. I just said 100, 100, 100 for the 3 L's. That leaves 300, 150 on each. What's the area? Multiply them, you get 15,000. Dollars. Square feet. Now, which is a better design? We're not going to get into the aesthetic appearance of the enclosure. We're just going to say that the first design is better because you get more area. And I've seen this question. In fact, I seem to recall having to do it in an exam in university, where it just told you that information and said that the fences have to be parallel and perpendicular to the barn. What's the maximum area? And you did not get full marks unless you investigated both possibilities and then said the first one is better. Any questions with that set of examples? Find two positive numbers whose product is 80 and whose sum is a minimum. So they're positive, okay. Well, I mean, maybe I better hold off here for a second. Are we going to use x? I don't know. We have two numbers. We need to define them. I'm going to say, I'm mixing up what we were doing just today in Math 20, which is max mins, with this, which is max mins. I'm going to tell you to avoid x for a variable. Because the issue is, if you use, say, x and y as variables, sometimes your y variable ends up being on the horizontal axis, which is fine. You would have d something dy, but it just rubs you the wrong way a bit. So I'm going to say that those are the two numbers. A plus b is the sum. So what I've written here is an equation relating the two variables and a second equation relating the two variables. But this is the constraint. This is to be optimized, right? So what we're thinking here for this function is s as a function of either a or b, and we need to get rid of a or b. Well, we use the equation of constraint. I'm going to get rid of a. It really, really doesn't matter. A is 80 over b. This means I just want to organize my workspace a little bit here. This means that our function now is s, which is to be optimized, is a, which is 80 over b, plus b. To make sense of this so that differentiation isn't, well, to make differentiation as easy as possible, let's move that b up top, and we're ready to go and finish the problem. ds db equals negative 80 b to the negative 2 plus 1. How do you solve this? Factor. Listen, I've said this before, I'll say it again. What I'm going to put in green, don't do this. Don't write equals 0 and solve it as an equation unless you need to. Okay? Instead, factor and look at the factors. I can take out of that.
Attention, the hold and secure has ended. The hold and secure has ended.
I would take out the negative. I don't think you need to take out the negative. I don't care for a leading coefficient that's negative. That leaves me with 80 minus b squared. Kind of weird that I have to think about that quite a bit for some reason because of where the 80 is, but I believe that's right. If you multiply that back in, you'll get the result. Are we okay with that? Okay. Which means that ds db is negative 80 minus b squared over b squared, which means here come our critical values for b. Positive root 80, negative root 80, and 0. The fact that you were told they are positive numbers means b must be greater than 0, and that means you exclude 0, you exclude the negative of the square root of 80. The only critical value for b that survives is that. which means that must be the value of B. What is the value of A, the other number? Well, A is equal to, didn't we say it's 80 over B? Which is 80 over root 80. If you rationalize that by multiplying top and bottom by root 80, this is 80, which cancels with that 80, which means A is also root 80, which intuitively kind of makes sense that the sum is going to be as small as possible if the numbers are as close together as possible. It may not make sense to you intuitively, but if I were to take 1 and 80 and add them together, I'm going to get a bigger sum than, say, 2 and 78. Do they? Oh, they don't add to. If I were to take 1 and 80, the sum is quite large. If I were to take 2 and 40, the sum is smaller. Okay. And one more, and I'll let you know what's going to happen here. This will be the last example today, and tomorrow will be a practice day. So you're going to be doing some problems for tomorrow, but there's going to be a practice time tomorrow to do this stuff. An orange grove contains 60 trees per acre. So I don't know if you know how big an acre is, but it's a certain area of land, and they plotted 60 orange trees on there. And past experience says that you get, in the growing season, 500 oranges per tree. I don't know if this makes sense, but if you plant more trees in that same space, each tree is going to give you less oranges. It's because the oranges come from the nutrients in the soil, ultimately. Well, plus water and all that other stuff, sunlight, but if you start crowding the trees together more and more, each tree doesn't provide as much fruit. It's a fact. So the question is, how many trees should be planted in an acre to give the most number of oranges? Do you recognize this is the same as the concert problem? That you increase the ticket price and the revenue starts to go up, but then it starts to drop. If we increase the trees, the number of oranges, the yield goes up and then it starts to drop. So what we're going to do here is say x equals the number of extra trees planted. We don't want to use x equals the number of trees planted. It gets too complicated. Okay, what will your yield be? I'm going to use y equals yield, which is the total number of oranges in the acre in the growing season. That's going to be found by taking the number of orange trees I took Art 9, by the way. Mrs. Joyce. The number of orange trees times the number of oranges I know that's red and not orange, but I can't get the orange right now. Per tree. And I'm not going to draw the tree again because you laughed at me, so. Well, okay, so how many trees are there going to be? Well, we are already planting 60, and you're going to add X trees. So whatever X is, if the number of extra trees to optimize the number of oranges is 12, then we're going to plant 72 trees. The number of oranges per tree, well, currently we're getting 500 oranges per tree, not all at once, in the growing season. It's going to decrease by 5 oranges for each extra tree. Well, the number of extra trees is X, so it's going to decrease by 5X. The rest of the problem is really simple. FOIL it out, differentiate it, and I hope you understand, with the exception of the previous example, all of our functions today have been quadratic, which means all of the derivatives are linear, which means finding a critical value is easy. So we FOIL this out. Some of you I can see are way ahead of me here, and that's great. I'm going to get negative 5x squared, which tells me it will be a parabola opening down, which is what I want for a maximum. I'm going to have plus 200x. Can anybody confirm that the outer and inner will give me a total of 200x? Good. And my constant term will be 60 times 500, which is 30. I didn't carry as many decimals last time as I should. I think it's 30,000. And sorry, I almost said, now we have to complete the square, because we just finished that in 20-1. No, we differentiate it, find the critical value of x, and answer the problem. dy dx is negative 10x plus 200. I mean, I think you can see that the critical value is 20 without maybe even factoring or doing anything. But if you factor out that negative 10, you're left with x minus 20. One critical value of x at 20. There's a little bit more involved than just hand waving it away and saying that must be the maximum. The function has to exist there, but the function is a parabola. It's a quadratic function. It's a polynomial which exists everywhere. So of course the function exists there. The only explanation here then is that at this critical value, dy dx is equal to 0, which means it looks like that, which means that's the maximum yield. So I don't feel as though I need to write everything down now. You have to plant 20 more trees. So be careful, because if the question said how many trees per acre need to be planted, the answer is 80. Because you started off with 60 trees and you're planting an additional 20. If the question says then, I guess I'll write it down. Don't be so lazy, Paul. 80 trees per acre. If the question asked now, how many oranges per tree will you get in the growing season, you would go back to the fact that you're losing 5 oranges for every x. So if x is 20, you're losing 100, and we started off at 500. Oh. This will lead to 400 oranges per tree. If you want to find out the total number of oranges, if you're just blindly looking at the equation, you could put 20 in here. Or you could take 80 times 400 and get 32,000. Per acre, per growing season. So as I said, today we're just getting a start on this. What you do is and I will leave this up for you, you develop an equation that relates whatever you're trying to optimize to one other variable. You find d variable to be optimized d other variable. You identify the critical values, and it will be a number of days before you encounter where you have to use a first derivative table. Because all of these problems, I believe, are just going to give you one critical value of x, or the variable. So yeah, then you differentiate, find the critical value. If you need to look at the domain or the first derivative chart. Like that one example, we had 3 critical values, didn't we? But we tossed 2 out because it was in the wrong domain. Here are some to practice.